Okay, so yeah, so the main agenda for today is like we'll go through the introduction of the distributed system, the characteristics and the types of distributed system, and also the best practices. We'll also look into some of the design patterns for the cloud distributed systems. Yeah. So the general way how this works is like you basically have multiple nodes which are placed in different locations, and then you communicate through these nodes over the network. So that's the difference between like having a centralized system and a distributed system. So now we're going to talk more about the characteristics of the distributed systems, right? So there are like many, but generally like four of them comes to my mind when I talk about the characteristics. So let's look at each one of them. The first one is the service discovery. So basically, this is as the nature of the distributed systems is that you have multiple services that are interacting with one another, and they are completely decoupled. They are not in the one location, they are completely decoupled. So you need to know how the service gonna communicate with other ones, right? So somehow they have to discover the other service. So let's say you are scaling up or scaling down on one services dynamically, and now how will you able to communicate with them, right? So that's how the service discovery is basically off. So there are multiple different ways to actually do the service discovery. So one of it is DNS based discovery, and the other one is client side and the server side. So in the DNS based discovery, what you do is basically you use the domain name service to map service names to IP address and ports. That allows services to discover each other's location. And for the client side discovery, you involve the client. So basically the client has access to some sort of a registry with all the list of all service locations. And based on that, it will identify which service to invoke. And similarly, this is on the server side. So it will maintain a centralized service registry where all the services can come and register themselves. And then you can query that registry to discover other services. So the next slide is on the load balancing. So yeah, so this is also another key important aspect in distributed systems when it comes to like load balancing, right? So how you are planning to distribute your load to multiple different systems. So you don't want to, if you don't distribute the workloads properly, right, then you have this problem of using only one server, and you will be prone to cause some server failures, and there will be a performance impact as well. So there are like basically two types of load balancing, static and dynamic. The static ones use a predefined set of rules to distribute the traffic, while the dynamic one, it quickly adapts to the change in the traffic volume, load, and the server availability. And based on that, it will pick whichever service is available. It will automatically do the load balancing. So there are a couple of like pretty good commonly used algorithms are there, like round robin is there, where it will distribute the traffic evenly among the group of servers in a circular manner. And then there's something called least connection algorithm, which actually distributes the incoming traffic to the server with the fewest active connections. So let's say only one server is taking care of the load currently, and there are other servers with the least active connections, then it will distribute the traffic evenly to target those servers. So that way you're preventing any one server from being overwhelmed and reducing the downtime. And there's something called a DNS-based algorithm, which again uses the IPs and the domain names to distribute the traffic. So it quickly resolves different IP addresses or servers, and based on that, it will redirect the traffic. So there are the industry standard ones are already available. Like I would always recommend not to reinvent your wheel. Whatever is available out of the box, like you can use the Azure Load Balancer, Service Mesh. If your application is containerized, use Kubernetes. It provides the built-in load balancing for distributing node across multiple pods of services. So whatever is available, rather than reinventing the wheel, make sure you use the industry provided products. So the next one is distributed tracing and logging, right? So this is very important because, like you have multiple services now in the it's intertwined in the distributed systems architecture. Now you wanted to make sure that how your requests are coming into your system. Like if there is any issue or any service is down, right? So you need to make sure that you have the ability to look at the logs and also the request to identify any bottlenecks. And if there is any issue, you should be able to debug it quickly. So that's where the importance of the distributed tracing and logging comes in. So there are a lot of open source distributed tracing systems available. Like you can use Zipkin, Zeiger. If you're going with the distributed logging, you can use Elk Stack also. So this way, it will really help you to process each and every event that is occurring in this system. And when you combine both the distributed tracing and logs, right? So you can easily identify any bottlenecks, go through the diagnosing those errors and enhancing that overall system performance is good. So, and I should really appreciate the way that the .NET Aspire team, they have built this dashboard. So this comes by default. Like if you are today, if you are creating any .NET core web application, right, with onboarding to the Aspire, it will by default give you a dashboard where you can go and look at each and every trace request. You can identify how your services are getting called, from which IP address. All these details will be available right out of the box. You don't have to do anything. And it's an easy way to identify if there is any services having trouble. You can look at those logs and identify if there are any latency issues. And the fourth one is on the service monitoring. So service monitoring is very important because like now you have all these distributed systems connected over the network. What happens if one of the service goes down? So you need to have some sort of way to find the health of the systems, right? So for that, right, we have a lot of tools available. Again, like Prometheus is there, Grafana dashboards are there. So in our systems also, we use Grafana dashboards where we identify the node health and make sure if the nodes are down, we will trigger some sort of notifications to our teams, and we will also create some incidents. And based on that, we will identify this bottlenecks and we will fix it right before our customer or somebody complains. So when building the distributed systems, make sure that service monitoring, like you have to understand the importance of health of each and every system. As long as you are getting this notifications and managing the health, I think you will have a reliable distributed system. So let's look at some of the key benefits of using the distributed systems. So the first one that comes to your mind is like, the scalability, right? So there's different scalability options that are available. So you can do vertical scaling or the horizontal scaling. So vertical scaling is basically, it involves increasing the hardware resources of a single machine, which is often limited by the physical constraints, because there is some sort of a restriction for you. Like you cannot go maximum number of cores or memory capacity other than it supports by your system, right? But when it comes to the horizontal scaling, so instead of increasing your system, now you can add in more systems to your service, and you can scale out. So that way, if there is any new load, or if there is a system failure with one service also, you can automatically make use of the other systems in the service. So that's the advantage you get with the distributed systems. And there is something called reliability, right? So the distributed systems are more resilient to failures compared to the centralized systems. Why? Because the data has been replicated across multiple nodes now. So the failure of a single node or a subset of node does not necessarily bring down the entire system, because automatically the failover happens if let's say you are doing some sort of a master slave architecture where there's one primary node, all the traffic is actually handled by that particular primary service, and then there is suddenly some sort of non-transient failure. So automatically you'll fail over to the secondary one, but still the system will be handling to the user request. So the overall reliability of the system is there when you choose the distributed systems. And the next one is basically on the performance. So as long as you involve breaking down your complex workloads into the smaller manageable parts, right? now you take advantage of this multiple machines. So sometimes you can distribute your work into small chunks where the primary will be handling some task, and then there are active secondaries which are like initially it can be idle, but then if you have a complex task like doing some sort of large scale data processing, or going through millions of logs on your local system or a centralized network share, now you can take advantage of the secondaries also. So that's how you will get more improved performance. And yeah, so let's look at some of the distributed system patterns. So here there are like a lot of them, but I've captured like some 7 to 8 which I use regularly, and the most common ones. So I'm gonna go through each and every design pattern, and let's analyze more. So the first one is basically on the ambassador pattern. So think like, let's say you're working as a director in a big company where you have a personal assistant who takes care of all the appointments, all the communications. So everybody who wants to book some time with you, they will first go through the personal assistant, right? So that is nothing but your ambassador pattern. So you have your application code, and then you will develop another um, service which actually handles your application code to do logging or monitoring or retry service. So all the communication acts or goes through via this ambassador. So it's just like a gateway, and it provides a simplified way to manage communication between the services. So yeah, so that's about the ambassador pattern, and the benefits you get is like reduce latency, enhance security, like the overall architecture of your distributed system is also improved. But if your service grows, right, then it only works for the smaller distributed service. But as soon as your network, as soon as your distributed service grows, then this has some bottlenecks also. So let's look at the second one. Second one is my favorite one, which is a circuit breaker pattern. So this circuit breaker pattern is actually used in distributed systems to prevent cascading failures. So cascading, so there are two types of failures, right? So one is the transient ones, and the other ones are non-transient ones. If it is a transient ones, it can quickly recover, and you can do just retry policies, if maybe a linear one or an exponential. Some of the other time it will come up. So that is non-transient. That is the transient ones. But for the cascading failures, which are the non-transient ones, there you need to have a system to identify. Okay, if I make a call to this continuously, even though the system is down, right? If you're making continuously calls, you're just simply wasting your resources. So that's where the circuit breaker pattern comes into picture. So it is basically used in conjunction with the retry pattern and the timeout pattern. So the beauty of it is basically it has like three states. Let me go to the next slide. So yeah, so it has three states here, which is the closed, half open, and open. So consider that when the state is closed, that means it is connected. So whatever the calls that you make from service A to service B, it will always go through and you will get the response back from service B. But let's say for some reason, service B, actually the performance or because of some issue, it went into non-transient failure, right? So this is down now. So even if you're making continuous calls from A, you're not going to get any response. So that's where you can plug in the circuit breaker, where it will automatically change the state from closed to open, right? Because it has reached certain failure threshold. So there's no point in now invoking that service. So it will go to the open state, and then based on the timeout, like, let's say if you expect the service to be back online again in half a day or in 1 day, right? Then you can add some timeouts. And if the timeout has expired, it will again check. So in order to check, now it will change its states to half open. And then it will try to make another call to service B. If at all, if the service B comes back online again, then based on the success counter, it will again go back to the closed state, and it will close that complete path. If at all, if it doesn't get the enough threshold, it will automatically go back to the open and it will open. So this way you're basically not wasting your resources. So as long as you know when the service is down, and if it is a non-transient ones, circuit breaker pattern will definitely help you in not wasting your resources. Yeah, and the third one is basically the CQRS pattern. So this design pattern that basically separates the read and write operations of a system. It allows for better scalability and performance by optimizing the system for each type of operation. So consider you have a big Amazon e-commerce application, right? Where you see like lot of read, like a lot of people will be browsing through the products, and then if they like any product, they will add into their cart, and then they will purchase a product. But the user traffic is more on consuming, like the reading and going through the products compared to actual purchases, right? So that's where you can actually segregate your workflow, where you can write a separate handlers for doing the command invocation and separate for query invocation. So that's how you will separate the read from writes. And then from the database side, you also need to maintain eventual consistency. Like if there has been any operations on the right side, you just need to make sure that you have the entire data flowing into the read database as well. So that's how you'll maintain the consistency. But if you look at the architecture, your code looks really good. Like if you're jumping into any project with a lot of distributed systems, when you separate your methods and separate your calls into the CQRS pattern, it's so easy to follow. Yeah. And the next one is the leader election pattern. So here, what you're trying to do is you have bunch of nodes, right? So each nodes will actually try to elect a leader. So this leader node is responsible for coordinating and executing tasks. It is used to actually build highly available systems which can tolerate failures. So what happens is, when, if at all, if the leader node goes down, then again all the nodes will try to elect a new one. So the main advantage here is all the exchanges, all the decision making, everything happens via the leader node. So that way you can avoid conflicts, and the decision making is completely owned by the leader node. And the next pattern is on the event sourcing pattern. So this is also very important one, where what happens is basically you have some changes in your system, right? So you handle those system changes as events. So it keeps a journal of all this live events, whatever is happening in your system, and it makes a record into this journal. So that way, when you want to actually go back and do some sort of auditing or do time travel debugging, let's say some issue happened in your system, if you want to identify, rather than just updating the database record, if it's showing the actual event, what is happening, right, then it's an easy way for you to debug and understand what exactly happened during that point. So one main example is think about the Git version control, right? So where you for every commit that you do, it will actually present a change. So it's easy for you to actually look at each and every one's change, and it also gives an ability for you to revert back, and without losing your changes or without having any conflicts. So similarly, in the distributed systems world, you can use the event source pattern for that. And the next one is the publisher and subscriber pattern. So yeah, most of the distributed systems, like, in one or the other way, they use the pub/sub model, where it actually decouples your systems. Like you don't have to worry about who is your publisher, who is your subscriber. So some sort of information is actually published into this the event center or event broker, where it will handle all the messages coming in, and then whoever wants to listen to it, right, so they will go and they will subscribe to it. And one beautiful advantage that you get is, like, let's say you have multiple distributed systems where you went ahead and changed your profile name and picture in the main portal, right, in let's say in your profile page. this should be automatically reflected in multiple different services or the systems. Even if you go to any other page, right, it should automatically get reflected. Why? Because it will make this change and it will submit this information into the event broker or event center, and then whoever has subscribed to this, they will automatically get a notification, and then they will look at this message, and based on that they will automatically change. So that's the beauty of publisher and subscriber model. So let's look at some of the types of distributed systems, right? So there are multiple, but I've captured like the most used ones here. So there's something called the hub and spoke architecture. So where it's actually it's very simple and efficient way to manage the communication in a network, because there will be like a central hub. So all the communication happens via the central hub. So which makes it easy to manage, secure, and troubleshoot. But as soon as the system grows, right, then it will also become a single point of failure. So there will be a bottleneck. If the system is small enough, then the hub and spoke model works for your needs. But as soon as the system grows, then it becomes a bottleneck. And the other one is the peer-to-peer. So in the peer-to-peer, right, so basically there's no central hub. All nodes are intertwine, they communicate with each other directly. So the problem here is like the challenge is to actually how to manage and handle, right? So every node is like, able to directly freely go and talk to each other. Let's say you have some centralized database where you need to update information. Now it gets trickier because the communications is happening node to node, so other nodes are not aware of it. So sometimes there is a problem with the eventual consistency, right? So you'll not be able to keep up the data so that other nodes can actually look into it. So it works for the smaller systems, basically. And the third one is the messaging queues, right? So this is a highly scalable architecture where messages are sent to the queue and then consumed by more consumers, like exactly what we discussed in the pub/sub model. So this provides more scalability, because if you want to increase your consumers, you can go ahead and do that. Even if you see a lot of publishers publishing the message, you can also scale publishers without impacting the consumers. So that's how you'll get more scalability and flexibility. And this is like, one of the commonly used type of distributed systems. And the last one is like hybrid, like mix of all. So based on your requirement, like I've seen people doing, mix of both worlds. They have used like, hub and spoke architecture for controlling the control traffic, and for peer-to-peer architecture, they use for data traffic. So as per your needs, as per your requirements, you can mix and match other types of distributed systems also into one. So now let's get into cloud. Like now you have understood the distributed systems and the types and everything. So now when you're designing for the cloud, right? So you also have to make sure few things, like for the cloud providers, when you think about the scaling, right? So let's say you have created some sort of batch nodes where you are getting new nodes based on your traffic. So you can write some sort of formulas where, based on the node, based on the load on your the batch node, you can automatically scale up or down. So you can also make sure that you control the cost efficiency, but also at the time when the load is very high, you should be able to scale up and uh, uh, maintain that load health. So that's how you can basically think about the auto scaling. So it has like more benefits, like you can improve your application availability, and also risk of any performance issues or downtimes due to the sudden traffic spikes. And the next one is about the health checks. So when you have this distributed systems, right? So as I mentioned, maintaining the health check is very, very important, because if at all, if you don't know if there is any system that is actually went down because of some issue, right? Then how do you actually recover from that? How do you know that there is some actually a problem in a system, right? So that's where the health checks are very important. There are multiple different ways you can do, like active and passive checks, but what you can do is basically make sure you have your systems in such a way that there's some sort of monitoring, some sort of health checks happening. Like if you go ahead with some of the industry standard products like Kubernetes or Service Fabric, where they will automatically publish the health event. They will tell you that, okay, there is some problem in actual node, and you will automatically see those nodes getting into warning or error state. And that's when you have to plug in your services to look into those errors and quickly recover from there. So the health checks is very, very important. And the next one is security. So when you're dealing with cloud, right, so make sure that you follow the best practices in terms of security. So wherever required, you need to encrypt your data. Make sure that you need to prevent any unauthorized access. The access controls, like when you're dealing with the storage accounts or the passwords or anything, use AKVs, or try to avoid using the SAS keys for accessing the storage accounts. And make sure you do the threat monitoring. So this helps to identify any security threats early in building your system, and based on that you can actually address and you can improve your system. So the security is a key aspect when dealing with the cloud-based distributed systems. Yeah, and the next one is the fault tolerance. So this is basically it's an ability for the system to operate even in the event of a failure. So some practices are like, you can go with redundancy, where it's one way of, like, making sure that you have fault tolerance in the system by having multiple instances of critical components. So the system, what happens is, like, even if one fails, then it will automatically fall back to the other ones. So that's how you'll make sure that there is always, even in the event of failure, your system is able to respond to the user request. And then you have failover mechanisms, which are like basically it will identify in case of the failover, right? So it will automatically switch the backup system. So how do you do that with a minimal downtime? That's what matters, like when you're building distributed systems. And again, the monitoring for the failures, this is the key part, where you have to make sure you detect these issues, notify the users or the admins of your system, and then make sure that you don't cause a significant problem. So that's how you have to design your systems, addressing the fault tolerance. And yeah, coming to the performance optimization, right? So yeah, so this is also another key part, where you want to make sure that your cloud systems are and operating efficiently and effectively. So the few ways of doing this is basically using the caching as a technique, where you improve the overall system performance by storing the frequently accessed data. Like you can make use of Redis cache, or most of the databases now have the caching ability in them. So you can make use of them and reduce the expensive and time consuming data operations. And yeah, so there's something called for even for the data access also, right? So you can make use of some of the techniques like indexing, prefetching, and minimizing the network round trips also. You don't have to make a call to your database every time you want to retrieve some information. So if it's non-changing information, you can maybe store it in your cache and make use of that cache every time, rather than hitting your database. So that way you can avoid some network round trips. And yeah, so I think that's a wrap.